In the center of every galaxy lurks a silent force that can erase stars, shatter time, and warp space into knots. What begins as a dying star ends as a hole in reality, a place where the known laws of physics surrender. Here, time stretches like taffy, space folds like origami, light itself is trapped forever. But what if this isn't destruction? What if it's a doorway to another universe, to the origin of time, to the hidden code behind everything? The deeper we look into these voids, the more they begin to look like the source code of the cosmos. And one question refuses to die. What if black holes don't just end things? What if they begin them? This is not science fiction. This is the frontier of reality. Stay with us. It all begins now. In the black silence between the stars, there are places that do not shine, not because they lack light, but because they devour it. Imagine floating near one, a region of space where even the glow of a dying sun is swallowed whole, where the very notion of escape has no meaning. It does not glisten, or radiate, or warn. It waits, and when it feeds, it erases. This is a black hole, not a thing, but an absence, not a surface, but a boundary, a limit carved into the fabric of reality itself. Black holes are born in death. When a massive star exhausts its nuclear fuel, it no longer has the strength to resist the crushing pull of its own gravity. The outward pressure that held it open vanishes. Gravity, unopposed, turns inward. The star collapses, not like a building or a mountain or even an imploding sun, but like a concept collapsing into contradiction. The atoms are squeezed into nuclei, the nuclei into quarks, the quarks into question marks. There is no material left, only a gravitational wound in space-time, steep and permanent. We call the outer edge of this collapse the event horizon. It is not a wall. You would not feel it as you crossed. But once inside, the universe beyond becomes unreachable, even at the speed of light. To fall into a black hole is not to crash, but to vanish from all possible futures. The pull of gravity here is so complete that it does not just affect objects, it distorts time itself. Clocks slow as they approach. The closer you drift toward the event horizon, the slower your moments pass relative to those far away. If someone watched you falling in, they would never see you land. You would appear to slow, to pause, to freeze on the very edge, your last breath stretched into eternity. From your own point of view, though, you would fall effortlessly through, in real time, 1 second per second. The black hole does not resist your entry. It simply closes behind you, sealing the door to the rest of existence. The idea of such a thing, a prison from which even light cannot escape, is not modern. As early as the 18th century, scientists like Jean-Michel and Pierre-Simon Laplace were already imagining dark stars, so massive that light itself could not break free from their surfaces. But these were thought experiments, curiosities based on Newtonian gravity. They didn't have the math to describe what lay beyond, and frankly, they doubted such absurdities could be real. It wasn't until Einstein reimagined gravity, not as a force, but as the bending of space and time, that black holes were given a home in physics. In 1915, his general theory of relativity rewrote the rules. Space could curve, time could stretch, and in that new geometry, it was possible to imagine a point of such immense compression that all paths bent inward, a place where all trajectories, including light, ended not in infinity, but in confinement. 1 year later, Karl Schwarzschild, a German physicist serving on the Eastern Front during World War I, found an exact solution to Einstein's equations. In the middle of war, with shells overhead, he penned the first mathematical description of a black hole. He died shortly after, never knowing the future he had unlocked. His solution described a sphere in space, defined only by mass, where the escape velocity reaches the speed of light. This radius, now called the Schwarzschild radius, marks the boundary of the black hole. Compress any object within that limit, and it becomes invisible to the universe beyond. But even then, scientists doubted. They believed nature would prevent such monstrosities from forming. Surely something, they thought, would intervene. Quantum pressure, nuclear reactions, entropy itself. Einstein himself believed black holes were mathematical fictions, not physical inevitabilities. Nature, however, is not obligated to match our comfort. By the mid-20th century, theoretical work from Robert Oppenheimer, J. Robert Snyder, and later Stephen Hawking and Roger Penrose began to show that under extreme conditions, black holes not only could form, they must. And now we know they do. We've heard their collisions echo through the universe as gravitational waves. We've seen their shadows burned into the light of swirling gas. We've mapped their grip on the orbits of stars, spinning madly around something they cannot see. The invisible has been measured. But what is inside? Here lies the true terror and the true wonder. Inside the event horizon, space and time switch roles. What was once distance becomes duration. What was once movement becomes fate. In this curved geometry, you do not fall inward through space, you fall forward through time, and all paths lead to a singular conclusion, the singularity. The singularity is not a place in space, but a moment in time. It is the end of where and the end of when. General relativity predicts an infinitely dense point where curvature becomes infinite and the laws of physics dissolve into incomprehension. It is a limit beyond which our knowledge and perhaps reality itself cannot proceed. But there's a problem. Infinity is rarely a real answer. In physics, when infinities appear in an equation, it often signals the breakdown of the model, not the truth of the universe. And so the singularity may not be a destination at all, but a signal, a cry from reality that something deeper remains to be found. And here is where our story deepens. Because the black hole does not just challenge our understanding of gravity, it requires us to unify it with something else entirely, quantum mechanics. And the moment we attempt to merge these two realms, the cosmic and the microscopic, the black hole becomes a battleground for the very foundation of reality. But for now, in this beginning, we stand just outside the veil, peering into the gravitational silence, listening for clues, a place that takes in mass, time, light, and information, and offers no return. A star that collapsed into silence. A silence that speaks volumes. And so we ask, if black holes erase what falls into them, what becomes of the universe that created them? The journey into that question begins now. It began, not with gravity, but with escape. In the 18th century, long before anyone imagined bending space or evaporating black holes, two men dared to ask a question that seemed as strange as it was beautiful. Could light itself be trapped by gravity? John Michell, an English clergyman and natural philosopher, first proposed the notion in 1783. Working from Newtonian principles, he calculated that if a star were massive enough, so massive that its escape velocity exceeded the speed of light, then light itself would never escape its surface. Such an object would be invisible, not absent, not non-existent, but hidden, cloaked in its own gravitational pull. A few years later, across the English Channel, the French mathematician Pierre-Simon Laplace arrived independently at the same idea. In his 1796 treatise, Exposition du Système du Monde, he wrote of dark stars whose mass was so enormous their light would be lost to space. Both men were speaking in terms of Newton's gravity, a force acting instantaneously across a void, indifferent to geometry or time. They had no knowledge of photons, no understanding of relativity, no concept of the quantum, and yet somehow they had glimpsed a ghost of truth. But their idea, though fascinating, did not survive the 19th century. As the wave nature of light became better understood and Newtonian gravity gave way to deeper complexities, the dark star became a discarded curiosity, an artifact of an outdated framework. Then, in 1915, everything changed. Albert Einstein unveiled a new vision of reality, general relativity. Gravity was no longer a force, but a feature of geometry, the curvature of space and time caused by mass and energy. Massive objects distorted the stage on which all things moved. Planets didn't orbit because they were tugged by an invisible thread. They followed the straightest possible paths through a curved fabric. A revolution, mathematical and philosophical. But even Einstein did not anticipate what would come next. In the very same year that Einstein published his field equations, a German physicist named Karl Schwarzschild, stationed on the front lines of World War I, found the first exact solution. Amid the horrors of trench warfare, he calculated the shape of space-time around a perfectly spherical, non-rotating mass, an idealized star. His solution revealed a startling feature. At a certain radius, known today as the Schwarzschild radius, space-time curved so steeply that nothing, not even light, could escape. It was a black hole. The term would not be coined for decades, but the mathematics had spoken. An invisible prison, a one-way door, a boundary where space tips into time and time becomes irreversible. Schwarzschild died shortly after, never knowing the legacy he had left behind. Yet, even as his equations hinted at this new object, the scientific community recoiled. Einstein himself was unconvinced. Others called the solution a mathematical oddity, a coordinate artifact, not a real phenomenon. It was simply too strange, too extreme, too unphysical. Nature, they reasoned, would surely prevent such absurdities from ever existing. This was a common sentiment. The great physicist Arthur Eddington famously said, "There should be a law of nature to prevent a star from behaving in this absurd way." He was referring to gravitational collapse, the idea that a star could fall inward without end, disappearing behind an event horizon and forming a singularity. Absurd, he thought. Nature was not that cruel. But nature has no obligation to obey our preferences. Throughout the early 20th century, a few bold thinkers pressed on. In the 1930s, Robert Oppenheimer, the future architect of the atomic bomb, alongside his student Hartland Snyder, explored the fate of massive stars at the end of their lives. Their calculations showed that beyond a certain mass, no known force could stop the collapse. Gravity would win. The core would implode, space-time would curve beyond escape, and the event horizon would form. It was the first serious theoretical treatment of what we now call a black hole. Still, doubt persisted. The idea remained mostly theoretical, haunting, but unconfirmed. It wasn't until the 1960s that the tide began to shift. In that decade, a series of groundbreaking papers by Roger Penrose, Stephen Hawking, and others brought black holes into the mainstream of theoretical physics. Penrose, in particular, proved that under very general conditions, singularities were inevitable outcomes of collapse, not exceptions, but consequences. If general relativity was correct, then black holes were not just possible, they were required. And yet, despite the growing mathematical certainty, observational proof remained elusive. No one had seen a black hole. How could you? They do not emit light. They offer no glow, no surface, no outline. But physics does not only move by what is seen, it moves by what must be. Astronomers began detecting X-ray emissions from regions of space with no visible source. Stars were seen orbiting invisible companions with incredible velocity, obeying gravitational pulls far greater than any ordinary object could exert. Entire galaxies seemed to swirl around invisible centers. Slowly, the evidence mounted. The impossible had become inevitable. The term black hole itself was only coined in 1967 by physicist John Wheeler, who sought a poetic yet precise phrase to describe the unseeable. The name stuck. Ominous, elegant, and true. Even as the concept gained traction, there were holdouts. Steven Weinberg, a towering figure in theoretical physics, once admitted he hoped black holes didn't exist. Not out of denial, but because their very existence made the universe so perplexing. Their consequences were profound, their mysteries deep, their mathematics unruly. To accept them was to accept that we did not yet understand the rules of reality. And that is precisely what makes them sacred. Black holes are no longer theoretical. We have now heard them. We have felt their mergers ripple through the fabric of space in the form of gravitational waves. We have seen their shadows carved into luminous plasma by the event horizon itself, first in the galaxy M87 and then at the heart of our own Milky Way. But the greatest proof may be this: we now depend on their existence to understand the universe at all. Black holes have become the crucible in which our deepest theories are tested. They lie at the intersection of relativity and quantum mechanics, of geometry and entropy, of time and information. They are where the cosmos becomes most like a thought. abstract, compressed, essential. And they began as whispers, in minds that dared to ask, what if light could fall and never rise again? Today, we know more, and yet more than ever we feel their pull, not just gravitational, but intellectual. They are puzzles without edges, locks without keys, questions that contain the blueprint of space itself. They began as impossibilities. Now they are our best clues. And so we turn our gaze toward the threshold they present, that strange border between the seen and the unseen. Just beyond it, time slows, light spirals, the known breaks, and something else, something deeper, begins to emerge. Imagine standing at the edge of time, not metaphorically, not in poetry, but literally. 1 foot outside, in the familiar world of motion and breath. 1 foot inching forward into a place where time itself surrenders. A line, invisible yet final. You don't feel it pass beneath you. You don't hear it crack or snap or shift, but it changes everything. This is the event horizon, the skin of the black hole, the boundary beyond which there is no return. Once crossed, every path, every direction, every future leads inward. Even light, that fastest of all messengers, cannot climb back out. The event horizon is not a wall. It has no surface, but it is absolute. From here on, the universe forgets you. But from your point of view, nothing unusual happens. Let's imagine you are falling, not being crushed or torn yet, just falling gently toward a black hole. From your perspective, space looks normal. You drift closer. Your heartbeat stays steady, the stars still twinkle in the distance. Even as you pass through the event horizon, you feel no jolt, no rupture. There is no splash in this crossing. It is seamless. And yet you are now on a path with no fork, a trajectory carved not in space, but in destiny. To an outside observer, however, your descent is a ghost story. They watch your approach from afar, safe in orbit or on a distant station. As you near the black hole, they see your movements slow. Every heartbeat takes longer. Your hand rising to wave goodbye lingers midair. Your voice, if somehow transmitted, stretches, deepens, redshifts into silence. As you reach the event horizon, you freeze in place, not because you stop moving, but because your time stops flowing. To the outside world, you become an image, arrested in eternity, clinging to the very skin of darkness. This paradox is not a mistake. It is a prediction of Einstein's general relativity, and it has been confirmed through observation. Time does not pass the same for everyone. It flows differently in different gravitational fields. This effect, known as gravitational time dilation, is subtle near Earth, but profound near a black hole. In fact, the closer you are to the event horizon, the slower time runs for you compared to the rest of the universe. In theory, you could hover just outside the boundary, and while only hours pass for you, centuries might race by in the cosmos above. The black hole becomes not just a trap for light, but a well for time. This strange behavior led early physicists to believe black holes might not even form in practice. If time slows infinitely at the horizon, they wondered, wouldn't the collapsing star appear to freeze in place forever? Wouldn't the universe only ever see a star slowly approach the critical radius, but never complete its transformation? That confusion held for decades, but it missed a crucial truth: perspective. From the star's own frame of reference, and from the matter falling inward, collapse proceeds normally. Time doesn't freeze from the inside. The event horizon forms, the singularity follows, but to a distant observer, that story takes forever to unfold. There are 2 clocks here, 2 truths, and both are real. This duality, that time can stop from one view and continue from another, is one of the most haunting aspects of relativity. It is not an illusion. It is not an error. It is baked into the architecture of the universe. And it becomes even more astonishing when we realize that, for certain black holes, the event horizon isn't just a barrier for light or motion, it's a boundary for knowledge. There's a thought experiment called the no-hair theorem. It suggests that from the outside, a black hole has only 3 observable properties: mass, charge, and spin. That's it. No matter what falls in, a piano, a planet, a poem, a civilization, all of its information is wiped clean. The black hole doesn't care. It absorbs, it remembers almost nothing. A billion unique objects collapse, and only a simple, indifferent shell remains. And so the event horizon becomes a curtain, hiding not just location, but identity. But what if information isn't truly lost? What if it's just encoded differently? We'll return to that question soon. For now, consider this. From the moment something crosses the event horizon, it is cut off from the rest of the universe forever. Not because of distance, but because of causality. No signal, no matter how fast or clever, can be sent outward. The past becomes unreachable. Only the singularity awaits, a point not in space, but in time, waiting at the end of every possible path. This inward pull is more than gravitational. It's directional in the deepest sense. Once inside the horizon, falling toward the singularity is no longer motion. It is the future. Every second brings you closer, no matter what you do. There is no hovering, no escape route, no up or down, just the relentless tick of geometry collapsing in on itself. And yet, even here, there are whispers of complexity. For rotating black holes, those with angular momentum, the picture becomes stranger still. Around them, space itself begins to swirl. This region, called the ergosphere, drags objects with it. You cannot remain stationary here. Space is in motion. The event horizon still exists, but the space-time outside it is twisted, like honey stirred around a spoon. In theory, energy can be extracted from this swirl via a process known as the Penrose process. It suggests that black holes might not only absorb, they might also spin themselves slightly lighter, flinging matter outwards in rare, precise ways. Already, the black hole is becoming more than just a void. It is an engine, a clock, a paradox. And the mysteries keep stacking. Because when you stare long enough at the event horizon, you begin to wonder, is this really a one-way door? Is information gone forever? Does the black hole erase history? Or is the story being written elsewhere in some subtle code on the edge? These are not idle questions. They are central to physics. The edge of a black hole is also the edge of understanding. And to resolve its puzzles, we must bring in another pillar of science, quantum mechanics, and ask how the smallest particles behave near the most massive prisons. Before we get there, though, return once more to the image of a frozen astronaut, locked in place above the event horizon. To you, they're still reaching out, suspended, never quite crossing over, but to them, time is flowing. They're already gone, already deep inside the singular future. This is the paradox of perspective. The cosmos is not the same for all observers. There is no universal now. And that truth, the relativity of time, is not just a feature of black holes. It is a truth of our own existence. Your head ages faster than your feet. Satellites must correct for time distortion to keep GPS accurate. Every second, your own clock diverges, ever so slightly from the clocks around you. But nowhere is that divergence more complete, more sacred, than at the edge of a black hole. It is not just an event horizon, it is a boundary of becoming, a veil of finality, a shimmering surface across which the past disappears and the future collapses into inevitability. You cannot linger there. You cannot send word back. You can only fall forward. And in that fall, reality bends to its limit, preparing to tell us something we were never meant to understand. It was once thought that black holes were final, that once something crossed the horizon, its fate was sealed, not just in body, but in meaning, that whatever fell in was lost to the universe forever, erased without trace, as though the cosmos itself had chosen to forget. And for decades, this was the accepted vision. Black holes as absolute endpoints, perfect one-way vaults, absorbing light, matter, time, and truth, never giving anything back. Then, in the quiet depths of the 1970s, a man in a wheelchair changed everything. Stephen Hawking, already battling the ravages of ALS, turned his mind toward the unthinkable. He asked a question that had troubled physicists for years. What happens when you bring quantum theory to the edge of a black hole? And what he discovered shattered the silence. Black holes, it turns out, are not entirely black. They glow. Not with fire, not with light as we know it, but with a subtle ghostly emission born from the quantum froth of the vacuum itself. A radiation that comes not from within the black hole, but from the very boundary that defines it, a whisper from the edge of the abyss. This glow is now known as Hawking radiation. To understand it, we must turn to the strange rules of quantum mechanics, rules that govern the tiniest grains of reality, far smaller than atoms. In this realm, even the vacuum, what we call empty space, is not truly empty. It seethes, it flickers, it breathes with the energy of uncertainty. At every point in space, virtual particles are constantly popping into and out of existence, tiny pairs of matter and antimatter, born from the quantum void, annihilating each other almost immediately. These fluctuations are normally invisible, ephemeral, but near the event horizon of a black hole, something extraordinary happens. Imagine a particle-antiparticle pair emerging right at the brink of the horizon. Normally they would find each other and vanish, but if one of them crosses the horizon before they can reunite, if one falls inward while the other escapes, the dance is broken. The escaping particle becomes real. It is no longer virtual. It carries energy away from the black hole, traveling outward into space. To an external observer, it appears as radiation, faint but unmistakable. And its partner, lost to the black hole's interior, carries negative energy relative to the outside world. And so with every such quantum escape, the black hole loses a tiny fraction of its mass. It shrinks. This revelation overturned centuries of belief. The black hole, once thought to be eternal, was now a mortal creature. Given enough time, vast stretches of time, far longer than the age of the universe, even the most massive black holes will eventually evaporate away, dissolving into a final puff of radiation. Let that settle in. The most perfect destroyers in the universe will die, not in fire, but in silence, not in collapse, but in evaporation, slowly, steadily, until nothing remains. But what of what fell in? What of the stars, the planets, the thoughts, the histories swallowed by the horizon? This is where Hawking's work did more than just illuminate black holes. It cracked open a paradox that still haunts physics. Because if a black hole evaporates completely, leaving only radiation, then what happens to the information it once held? In physics, information isn't just data on a hard drive or ink on a page. It's the arrangement of particles, the quantum state of a system, the story of what something is, and the laws of quantum mechanics are unitary, meaning in principle, information is never truly lost. It may be scrambled, hidden, transformed, but never destroyed. And yet, Hawking's calculation implied the opposite. If black holes vanish entirely, and if the only thing they emit is random, featureless radiation, then the detailed information of what fell in is gone forever. This is the black hole information paradox, one of the greatest unresolved questions in theoretical physics. If information can truly be erased by black holes, then quantum mechanics, the bedrock of modern physics, is violated. If, on the other hand, information somehow escapes, then we need a new understanding of how. The implications ripple outward, because if black holes can destroy information, so might the universe itself. If we can't trust the conservation of information, we can't trust the predictability of any system, anywhere, ever. It is not just a black hole's fate that hangs in the balance, it is ours. Over the decades, physicists have proposed many solutions. Some suggest that the information is encoded in subtle correlations within the Hawking radiation, a kind of quantum fingerprint, so faint and scattered it would take a perfect observer and an eternity of collection to reconstruct the original. Others believe that the information never leaves at all, but remains smeared across the event horizon, a kind of cosmic hologram storing everything that ever crossed its threshold. This idea that the surface of a black hole holds its secrets leads directly into the revolutionary concept of holography, which we'll explore soon. Still others propose that the black hole doesn't evaporate entirely, but leaves behind a stable remnant, a plank-sized core that contains the memory of everything it consumed. And some take a bolder step still, suggesting that information escapes through deep quantum connections, like entanglement bridges linking the inside and the outside. There is no consensus yet. but every path leads deeper into mystery. And all of it began with a glow, a whisper at the horizon, discovered not by telescope or probe, but by mathematics, pencil sketched across a notebook in a quiet Cambridge office. Hawking's radiation has never been directly observed. It is too faint, too slow, too patient for our instruments today. But it is almost universally accepted by physicists. It is embedded in the tapestry of theory. It changed how we see black holes. It changed how we see space itself. Because in order to radiate, a black hole must have a temperature. And if it has a temperature, then it must have entropy. And if it has entropy, then it must have microstates, internal degrees of freedom, a kind of structure, a complexity. But how can a black hole described only by mass, spin, and charge have such richness inside? That question is now at the heart of the next great leap, the search for a quantum theory of gravity, one that can unite general relativity's smooth geometry with quantum mechanics' granular chaos. Hawking's discovery is not the end of the story. It is the beginning of a new one, where fire emerges from darkness, where prisons glow, where death is not the last word. We now see black holes not only as graveyards, but as laboratories, natural experiments in the most extreme conditions the universe allows. They force us to ask the hardest questions: what is time? What is space? What is information? What is real? And they give nothing freely. Every answer must be earned, drawn out from the glow at the edge of silence. The light is dim, but it is there. And it tells us nothing in this universe is ever fully lost. Not light, not heat, not even secrets. Not if we listen closely enough. The universe, for all its elegance, is built on a tension that has yet to be resolved. On one side, general relativity, Einstein's masterwork, a sweeping theory of gravity that treats space and time not as a stage, but as living fabric, curved and shaped by mass and energy. It describes the cosmos with grandeur, from the orbit of Mercury to the collision of galaxies, from expanding space to the ghostly swirl of black holes. On the other, quantum mechanics, the rebel child of the 20th century, strange, unpredictable, beautiful. It governs the very small, atoms, electrons, photons, the jittering dance of existence at the most granular level. Where general relativity is smooth, quantum mechanics is discrete. Where one is geometric, the other is probabilistic. Where one follows strict causality, the other allows uncertainty, entanglement, even the possibility that a thing may not exist until it is observed. And for nearly 100 years, these two theories, the two greatest pillars of physics, have refused to coexist. Each works brilliantly in its domain, but when brought together, they fight. Nowhere is that battle more dramatic than at the edge of a black hole. Because a black hole is both a gravitational titan, warping space-time to extremes, and a quantum furnace, where energy, information, and entropy interact in ways we cannot yet describe. And so physics finds itself split. Relativity says one thing, quantum mechanics says another. Each is stubborn, each is precise, each is true. But the universe, evidently, does not accept division. At the heart of this tension lies a simple, terrible problem. We do not yet have a theory of quantum gravity, a single framework that unifies the geometry of space-time with the quantum behavior of particles and fields. Black holes, with their deep gravity and subtle radiation, demand such a theory. Without it, our understanding remains fractured. Let's follow the fracture lines. General relativity tells us that the singularity at the center of a black hole is a point of infinite curvature where space and time twist into oblivion. But infinities, in physics, are red flags. They signal a breakdown, not of reality, but of the theory describing it. Quantum mechanics, meanwhile, refuses to tolerate such infinities. At the Planck scale, the smallest possible unit of space and time, quantum effects become dominant. Gravity itself should become quantized. But general relativity doesn't know how to handle this. It is a classical theory, not a quantum one. When we attempt to merge the two, by calculating quantum field effects in the curved spacetime near a black hole, the math often explodes into paradoxes and contradictions. Probabilities no longer add up to one. Time becomes ill-defined. Information vanishes or duplicates. Logic bends. This is not a quirk, it is a crisis. And so physicists have spent decades crafting candidate theories, blueprints for a quantum theory of gravity. The two most prominent are string theory and loop quantum gravity. String theory posits that the fundamental particles of the universe are not points, but tiny vibrating strings, each mode of vibration giving rise to a different particle. These strings exist in higher dimensions, perhaps 10 or 11, most of which are curled up, invisible to our perception. In string theory, gravity emerges naturally, and black holes can be described as massive stringy objects, complete with entropy, temperature, and microstates. Loop quantum gravity takes a different path. It starts with space itself, attempting to quantize geometry. According to this view, space is not continuous, but woven from discrete loops, quantum threads of volume and area. In such a universe, singularities might be avoided entirely, as the grain of space prevents infinite compression. Both theories offer glimpses. Neither is complete. Both are bold attempts to reconcile the irreconcilable. And in the center of this theoretical war stands the black hole demanding answers. Stephen Hawking's discovery of black hole radiation was a first shot fired. It showed that quantum effects matter, even in the strong gravity regime. It showed that black holes have entropy, and that entropy is proportional not to their volume, but to their surface area. A result so strange, so profound, that it launched an entirely new idea, holography. We'll reach that revelation soon. But for now, pause with the paradox. How can the surface of a black hole store all the information of what fell in? Where does the information go during evaporation? If we ever hope to resolve these questions, we must find a theory that speaks both languages, curvature and quanta, determinism and uncertainty. This conflict isn't just about math, it's about reality. Because if we cannot reconcile gravity and quantum mechanics, then we do not truly understand the beginning of the universe. We do not truly understand the heart of stars. We do not truly understand what happens when matter falls inward, collapses, and confronts the very edges of what space and time can be. The stakes are enormous. Some physicists believe that black holes are the Rosetta Stone of quantum gravity, that by decoding their properties, their entropy, their radiation, we will uncover the grammar of a deeper theory. Others believe that the true theory may not resemble either relativity or quantum mechanics, but something altogether new, something that explains both as approximations of a more fundamental truth. And still, we are left with unknowns. What is space? At its core, what is time? Are they emergent? Are they fundamental? Is the fabric of reality made of information, geometry, or something stranger still? These are not questions for the curious alone. They are questions for the necessary, for the survival of any future physics that seeks completeness. And as we look forward, we must also look inward. Because the war between theories is not just out there, at the edge of black holes. It plays out in the tools we use, the models we trust, the assumptions we carry. It forces humility. It invites imagination. Consider the firewall paradox proposed in recent years, a radical claim that the event horizon might not be a gentle boundary at all, but a searing wall of quantum energy, a place where infalling observers are incinerated instantly. If this were true, it would violate the principle of equivalence in relativity, which says that crossing the horizon should feel smooth, uneventful. Another theory, EREPR, suggests a connection between two of the strangest ideas in physics, Einstein-Rosen bridges, wormholes, and Einstein-Podolsky-Rosen entanglement, quantum linkages across space. According to this bold hypothesis, entangled particles might be connected by microscopic wormholes. If true, this could mean that black holes and space itself are woven together by the threads of quantum entanglement. In this vision, space-time emerges not from geometry, but from information. But even that is just a whisper, a speculation, a step on a longer road. The black hole remains silent, stubborn, dark, challenging both our giants, relativity and quantum mechanics. And so, the war continues. Not in anger, but in longing. Not with explosions, but with chalk dust and code. With equations stretched across blackboards and silicon. This is the battlefield of tomorrow's physics. And the prize is nothing less than the foundation of reality itself. We turn now from the theories that clash to the paradox that refuses to die, the puzzle at the very core of black hole physics, where information seems to vanish and logic folds in on itself. The question is simple. What happens to what goes in? There are questions that echo forever, that defy closure, that lie like thorns in the mind of science, impossible to ignore, impossible to answer, persistent as gravity. And the deepest of them all may be this: what happens to the information that falls into a black hole? A planet, a book, a person, 1,000 years of memory, all spiral inward, crossing the event horizon, never to return. Eventually, the black hole evaporates, fades, disappears into the void. But where did the story go? This is not philosophy, it's not poetry, it's a scientific crisis, a paradox with teeth, a confrontation between the two great laws that govern everything. On one side stands quantum mechanics, which declares that information is sacred, that no matter the transformation, no matter the violence, the details of a system's state must always be preserved. You may not be able to reconstruct it easily. It may be scrambled, hidden, entangled, but it is never lost. On the other side stands Hawking radiation and the slow, irreversible evaporation of black holes. The glow that seeps from the event horizon is purely thermal. It carries no imprint of what fell in, no memory, no message, just heat escaping into the cold. And when the black hole finishes dying, it leaves no trace behind. This is the black hole information paradox. If Hawking's calculation is correct, black holes violate quantum unitarity, the idea that the evolution of a closed system is always reversible. It means that information can be erased from the universe, that causes have no effects, that entropy can increase without reason, that memory itself has boundaries. This cannot be. Or so say the physicists. Because if information can be destroyed here, it can be destroyed anywhere. The laws of physics are no longer trustworthy. Predictability collapses. The structure of reality built on cause and effect begins to crack. But what if Hawking's calculation was incomplete? What if something was missing, some subtle quantum detail he couldn't see, masked by the blunt tools of the 1970s? That possibility has become the obsession of a generation of physicists. In the years since Hawking's work, multiple ideas have emerged to explain how information might survive. Some suggest that the radiation isn't random after all, that it contains subtle correlations, entanglements that preserve the lost details in scrambled form. The pattern may be impossible to decode, but it is there, hidden in the glow. As the black hole evaporates, the outgoing radiation carries away, bit by bit, the record of what fell in. Others propose the idea of black hole complementarity, that to an outside observer, information appears to be preserved in the Hawking radiation, while to an infalling observer, it continues smoothly into the singularity. Two descriptions of reality, mutually exclusive, both true, like light behaving as both wave and particle. But then came the firewall. In 2012, a group of physicists, Almhiri, Marolf, Polchinski, and Sully, introduced a terrifying possibility that the assumptions used to resolve the paradox were incompatible. If information escapes in the Hawking radiation and quantum mechanics is unbroken, then the horizon cannot be smooth. Something must give. And so they proposed the firewall. According to this idea, the event horizon isn't a soft, invisible boundary, it's a searing wall of high-energy particles, where space breaks and time ends, where anyone falling in would be instantly incinerated. This violates Einstein's equivalence principle, which states that locally in free fall, the laws of physics are indistinguishable from those of empty space. According to relativity, you shouldn't feel anything at the horizon, it should be quiet, peaceful, unremarkable. But the firewall says otherwise. It says that quantum mechanics saves information, but only by sacrificing the calm geometry of space itself. This created a rift in the physics community, a deeper paradox. Now, three sacred principles could not all be true. 1. Quantum mechanics is unitary. Information is preserved. 2. General relativity is correct. The horizon is smooth. 3. No drama occurs at the horizon. Observers pass freely. Pick 2. One must die. Some hoped to resolve the paradox with entanglement, suggesting that the outgoing Hawking radiation remains connected to the black hole's interior, forming a bridge of quantum correlations that preserve information. This led to the bold proposal known as EREPR. Formulated by physicists including Leonard Susskind and Juan Maldacena, it links two famous ideas, Einstein-Rosen-Bridges wormholes and Einstein-Podolsky-Rosen entanglement. It proposes that entangled particles are connected by tiny, non-traversable wormholes, literal bridges in space-time. If true, then every pair of entangled particles is linked, not just in math, but in geometry. And black holes, massive, entangled systems, may be connected to their radiation through hidden quantum pathways. This could mean that information escapes through geometry, folded and curled in dimensions we cannot see. And still, some believe that the answer lies not at the horizon or within, but on the horizon itself. This brings us to the concept of holography. In 1997, physicist Juan Maldacena introduced the ADS-CFT correspondence, a bold idea from string theory that suggests our universe, or at least certain kinds of universes, can be described in two different ways, one with gravity in a curved space, the bulk, and one without gravity, defined on the boundary of that space. In this duality, every particle, every interaction, every black hole in the bulk, has a mirror description on the boundary. This means that everything happening inside a volume of space is encoded on its surface, like a hologram. And if black holes obey this principle, then all the information about what falls in could be preserved on the event horizon itself, stored in quantum bits on the surface. The black hole becomes a holographic projector, its interior a kind of illusion, its surface the true keeper of memory. This idea reshapes our vision of space and time. It tells us that volume is an illusion and that the true physics may lie at the edges of things. Hawking, late in life, began to accept this view. He proposed that the information is not destroyed, but rather preserved in a supertranslation imprint, a kind of quantum scar left on the horizon itself, from which it could, in principle, be recovered. But we are still far from certainty. Experiments cannot yet reach these scales. Black holes are too distant, too quiet. Hawking radiation is too faint to detect. The math is complex, the theories young, and yet, piece by piece, the paradox is being chipped away. One recent breakthrough came in 2019 when physicists used insights from quantum information theory to calculate page curves, graphs that describe how the entropy of a black hole's radiation should change over time if information is preserved. The results match the predictions of unitarity. It suggested that yes, information can escape, but only if quantum gravity effects are taken into account. The page curve rises, then falls, tracing the birth and death of the black hole and hinting at a deep consistency in the laws of physics. The paradox isn't solved, but it is changing, evolving. The very debate has reshaped our understanding of physics. It has pushed us to consider that space and time may not be fundamental at all, but emergent, born from deeper principles of information and entanglement. That geometry is a side effect of relationships, that black holes are not just things, but processes, dynamic, whispering, alive with structure. This is what the paradox teaches us, that the universe keeps its secrets not by locking them away, but by scattering them into patterns we cannot yet read. That even the darkest object in the cosmos might still be a book, just written in a language of heat and spin and quantum flame. That even in loss, there may be preservation. And so the question still burns. What happens to what goes in? The answer may not lie in one theory, or one equation, or one mind. It may lie in the harmony yet to come, when gravity and quantum, light and shadow, smooth and jittering, finally speak the same tongue. We move now to that hopeful future, to the idea that space itself might be an illusion, and reality a hologram, projected from the edges of the world. Crossing the event horizon is not a fall through space. It is a fall through destiny. Once you have passed that invisible threshold, your future is no longer a path you walk. It is a direction written into the structure of space-time itself. You do not fall toward the singularity. You fall into it, the way you might fall into next Tuesday or next year. Inside a black hole, the singularity is not just a location. It is your future, as inevitable as aging, as final as a last breath. There is no turning back, no orbiting, no pause. Every second, every plank tick of your falling frame draws you closer to that ultimate point, the place where space-time ends. But what is that point? We call it the singularity, the heart of the black hole, a region of infinite density, infinite curvature, infinite compression, a place where Einstein's equations break, where physics stops speaking, where cause and effect dissolve into silence. But that word singularity is less a description than a confession. It tells us, we don't know. We don't know what lies at the center of a black hole. We don't know what happens to space, to time, to energy, to information. We only know that the equations we've trusted, the same ones that guide GPS satellites, predict eclipses, and describe the bending of starlight, blow up. They yield infinities. They yield nonsense. This is not a minor glitch. It is a signal, a beacon, a sign that something deeper is missing. Inside the black hole, the curvature of space-time grows beyond measure. Tidal forces stretch and compress everything. In small black holes, these forces become lethal, well before you reach the singularity, stretching your body into strands, atom by atom, in the infamous process known as spaghettification. But in supermassive black holes like the ones at the centers of galaxies, the journey is stranger. The gravitational gradient is so shallow near the horizon that you might drift across it without noticing. No stretching, no crushing, no drama, only silence, only inevitability. And once inside, there is no escape. Not because you are trapped in space, but because the flow of time carries you forward, and all directions forward lead to the singularity. What happens there is unknown. Does space end? Is the singularity a point of rebirth, the beginning of a new universe, a bounce from collapse to expansion? Is it a firewall, a rupture in geometry, a place where reality shreds into quantum fog? Or is it something more radical, a place that doesn't exist at all in the way we imagine? Let us pause here, inside the black hole, and consider the nature of time. Outside, time and space are woven together, flexible, curved but distinguishable. Time has direction, space has dimension. We move through one, we sit within the other. But inside the black hole, that distinction inverts. The radial coordinate, the one that used to be space, the one that measured your distance from the center, becomes time-like. That means you cannot choose not to move toward the center. It is your future now. It is your next moment. Conversely, time behaves like a spatial dimension, still there, still present, but no longer flowing in the same way. This reversal is not theoretical. It is baked into the very structure of space-time, as described by general relativity. To fall into a black hole is to enter a universe where the geometry of existence is reordered, where cause and effect spiral into new configurations, where the compass of possibility points inward, and the end of space is the same as the end of time. Some physicists propose that the singularity is not truly a point, but a veil, a boundary, a limit beyond which our concepts no longer apply. That what lies there is not a thing, but a failure of description, a place where our language, our math, our metaphors all fail. Others imagine that something exists beyond the singularity, that the black hole interior is not the end, but a bridge. In this vision, the singularity could be a kind of cosmic throat, linking one region of the universe to another. This is the idea behind wormholes, theoretical tunnels through space-time, connecting distant points or even different universes. In certain solutions to Einstein's equations, like the Kerr metric for rotating black holes, these bridges exist mathematically, but they are unstable. Any disturbance collapses them. They may not be real. And yet, the math whispers possibilities. Some theories suggest that the core of a black hole is not a singularity at all, but a Planck-scale object, a tiny, dense core where quantum gravity reigns, where space and time become granular, where the smoothness of the cosmos gives way to something discrete, pixelated, shimmering at the edge of meaning. In loop quantum gravity, the singularity might be replaced by a quantum bounce, a rebound that births a new universe. In string theory, the strings that make up matter may stretch across the interior, avoiding infinite density, resolving the singularity into something richer, stranger, and stable. And some propose that the singularity is simply a horizon of knowledge, not a thing, but an edge, not a physical object, but a mystery written into the core of every black hole, a place not meant to be understood, only approached. But even without full understanding, the singularity teaches us. It teaches us that our theories are not complete, that gravity and quantum mechanics must one day speak the same language, that time may not be fundamental, that space may not be real in the way we think. It teaches us humility, that there are places in the universe where our knowledge dissolves. And it teaches us awe, that inside every black hole lies a frontier, a precipice beyond which meaning itself must be reimagined. Perhaps most hauntingly, it teaches us this. If black holes evaporate, if Hawking radiation carries away their mass, bit by bit, then what happens to the singularity at the end? Does it persist? Does it vanish? Does the interior ever truly form? Because from the outside, a black hole's evaporation is slow, patient, ghostly. But from the inside, time flows differently. The singularity might form in moments, or not at all. Some physicists suggest that the entire interior of a black hole, from event horizon to singularity, might be a kind of holographic illusion, a region encoded on the surface, never truly realized, never truly in there. If this is true, then the singularity is not just hidden, it is virtual. A story told by the edges, a punchline whispered by the fabric of space-time itself. And yet, we believe in singularities. Not because we've seen them, but because they arise, inevitably, from the theories we trust. Like fossils left by a physics we haven't yet uncovered. They remind us that at the heart of the cosmos, there are places where time ends. And in that ending, we are called to begin again, to invent new ideas, to push beyond the limits, to listen to the silence inside the fall. The singularity is not the end of our journey. It is the reason we journey at all. And so we continue upward now, back to the boundary, to the horizon itself, where the greatest secret may not lie inside the black hole, but on its surface. Where the universe may not be what it seems, but a hologram. Reality feels full, thick with form, flavor, sound, and light. We move through space, we age in time, we touch surfaces, we weigh things, we believe viscerally, confidently, that we live in a three-dimensional world. But what if that is a mirage? What if the depth of the cosmos, the volume of stars, the stretch between galaxies, the space between your fingers, is an illusion? What if everything we experience, every atom, every force, even the ticking of time, is just the projection of something happening elsewhere on a distant two-dimensional boundary? This is not fiction. This is the holographic principle, one of the most radical ideas in modern physics. And black holes, paradoxically, led us here. It all began with a puzzle, the entropy of a black hole. In classical thermodynamics, entropy is a measure of disorder, of how many microscopic configurations a system can have, even if it looks the same on the surface. For a gas in a box, entropy scales with volume. The bigger the box, the more room for atoms to jumble, the greater the disorder. But black holes break this rule. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered something astonishing. The entropy of a black hole is not proportional to its volume, but to the area of its event horizon. That means the more surface a black hole has, the more information it can hold. The volume inside, irrelevant. This was deeply weird. It was as though the contents of the black hole, everything it ever swallowed, were encoded on its skin, not inside, but on the surface, like a hologram. And that led to a radical leap. If the laws of physics for black holes are governed by surface area, not volume, Could the entire universe work the same way? This question was taken up with full force in 1997 when physicist Juan Maldacena proposed the now famous AED-CFT correspondence, a mathematical duality rooted in string theory. It says this: a theory of gravity in a higher dimensional space called AD-AS, anti-de Sitter space, is equivalent to a theory of quantum particles living on its lower dimensional boundary, CFT, conformal field theory. That's a mouthful, but the essence is staggering. It means that a world with gravity, curvature, black holes, time could be fully described by a world without gravity, living on a flat, lower dimensional shell. Everything inside is encoded outside. A hologram. This isn't metaphor, it's math. The two descriptions match perfectly. Every particle, every interaction, every twist of geometry in the bulk corresponds to something on the boundary. AD space is not our universe. It has negative curvature, unlike the flat or positively curved space we observe. But physicists believe the correspondence might point to something deeper, that our own reality might also be a projection from lower dimensional data. Imagine the entire universe, including you, your thoughts, your history, all encoded on a cosmic screen far beyond your perception. You are not in the universe. You are the projection of data stored on its edge. This is the holographic principle, and it arises naturally from the study of black holes. Because black holes force us to reckon with information. If everything that falls in is somehow preserved, it must be preserved on the horizon. The event horizon is not just a boundary, it is a storage device, a membrane that encodes the past. In this view, the black hole is a hologram. Its interior is real to the infalling observer, but unnecessary for a full description of physics. Everything can be computed from the outside. Nothing deeper is needed. This is wild, but it works. And not just for black holes. Increasingly, physicists believe the whole of space-time might be emergent, not fundamental, but born from something deeper: information, entanglement, quantum correlations on a boundary we cannot see. In recent years, researchers have made powerful connections between the geometry of space-time and the entanglement structure of quantum states. They've shown that if you take a network of entangled particles arranged just right, you can literally reconstruct a space. Curvature emerges, distances emerge, even gravity appears as a natural consequence. In this picture, space is not the stage, it is the actor, a consequence of relationships between bits of information, as if the entire universe were a giant quantum error-correcting code, a resilient structure that builds reality from redundancy and logic. And if space emerges, what of time? Some physicists believe that time, too, is not fundamental, that it arises from changes in entanglement, from the flow of quantum information. In the holographic view, time might be a bookkeeping tool, a way of tracking how one configuration becomes another on the cosmic screen. This raises haunting possibilities. If the universe is a hologram, what is it projecting from? If space-time is emergent, what is it emerging from? And if our reality is encoded on a boundary, can we ever access that boundary? Can we know what's beyond? We don't know, not yet. But the evidence is mounting. Calculations from black hole physics show that all the information inside a region can be stored on its surface at a density of roughly 1 bit per Planck area, the smallest meaningful unit of space. This is the Bekenstein bound. It sets a limit, not just for black holes, but for any physical system. It says the amount of information inside a region of space is not determined by its volume, but by the area of its boundary. This is more than coincidence. It suggests that our entire concept of space may be a mirage, that what feels like depth is just complexity, that what feels like position is just entanglement, that what feels like reality is just the shadow of something deeper. And black holes are the gateway. They are the places where this principle becomes impossible to ignore, where entropy, temperature, and gravity all converge on a single surface, where the laws of thermodynamics merge with the geometry of space-time, where information is preserved but not where we expected. This changes everything. It changes what it means to be somewhere. It changes what it means to be someone. Because if reality is a hologram, then you, your body, your thoughts, your dreams are part of a projection. You are real, but your reality may be encoded elsewhere. Your experience is full, but its source may lie at the edges of things. And yet, this does not diminish you. It exalts you. Because if everything is holographic, if space-time, memory, and meaning are all woven from the same quantum threads, then everything is connected. Everything is entangled. The boundary and the bulk are not separate. They are one. You are not in the universe. You are the universe, unfolding. Just as the black hole contains its history on the horizon, perhaps you too carry the memory of existence, encoded not in space, but in the structure of being. And perhaps, just perhaps, the story of the cosmos is not written across time, but across surfaces, shimmering with hidden logic, waiting to be read. From the event horizon to the cosmic edge, the universe whispers, "Look not within, but along the boundary." That is where the truth lives. Now we move to the threads that hold that truth together, the quantum bonds, the fragile correlations, the logic behind illusion, the code behind the cosmos. Beneath the skin of reality, something trembles. Not particles, not waves, not even strings, but relations. Invisible, silent threads that connect everything to everything else, that stitch space, time, energy, and entropy into a single, self-consistent quilt. This is the quantum code, not a language we speak, but one the universe does, constantly, quietly, without pause. And to understand the black hole, and perhaps the cosmos, we must understand these quantum threads. They are not material. They do not lie within space. They create space. They are the structure of entanglement, the invisible bonds that form when particles become intertwined in ways that defy classical logic. Entangled particles share information, even across vast distances. Measure one, and you know the state of the other. They are not just correlated, they are one system, no matter how far apart. Einstein famously called it spooky action at a distance. But entanglement is more than spooky, it is foundational. In recent decades, physicists have discovered something astonishing. The geometry of space seems to be built from patterns of entanglement. Take a set of quantum bits, qubits, and arrange them in a specific network of connections, a kind of woven lattice of entangled pairs. What emerges is a structure that looks, acts, and curves like a piece of space. This is not metaphor. This is math. It is known as tensor network geometry, a framework in which the very notion of distance emerges from how deeply qubits are entangled. No entanglement, no space. The tighter the entanglement, the closer the points appear. Loosen the entanglement, and they drift apart. Break it completely, and the space disintegrates. This is how space collapses, not by moving points, but by unweaving connections. This revelation comes from studies at the frontier of quantum gravity, string theory, and information theory, and it has forced a staggering idea to the surface. Space-time is not fundamental. It is emergent. It arises from quantum information, from how bits talk to each other, from how the universe remembers itself. Black holes, once again, are the proving ground. Inside a black hole, space and time behave unlike anywhere else. Yet the information, the quantum description of everything that has ever fallen in, must persist. If the holographic principle is correct, it is encoded on the event horizon. And if space-time is emergent, then that encoding is the black hole. This brings us to the idea that a black hole is a quantum processor, a system that performs computations on information, reshuffling, mixing, and entangling it in unimaginable complexity. The radiation that leaks out. Hawking radiation is not just heat. It may carry the encrypted output of this computation. At first glance, it looks random, but deep within it could be the fingerprint of everything that was ever consumed. We just don't know how to read it. This is where quantum error correction comes in. Originally designed for quantum computers, fragile devices that store and manipulate quantum information, error-correcting codes are techniques to protect that information from noise, loss, or corruption. Think of it like this: if you write a sentence in code and one letter gets smudged, the code still lets you recover the original message. In 2015, researchers discovered that the structure of ADS-CFT duality, the holographic universe, behaves exactly like a quantum error-correcting code. The bulk of space-time is protected against errors. Information that falls into a black hole is not lost, it is encoded redundantly on the boundary. If one bit is disturbed, the whole can still be reconstructed. Reality, it seems, is resilient. This means the black hole, far from being a simple prison, is a sophisticated information processor capable of storing, protecting, and perhaps eventually releasing everything it ever absorbed. It may take billions of years, the output may be scrambled beyond recognition, but the information is not destroyed. Now step back and consider the implications. If space-time is born from entanglement, if geometry is the shape of information, if black holes are quantum codes, then the universe is not made of stuff. It is made of logic. Not the logic of syllogisms and propositions, but the deeper logic of states, relations, and transformation. A logic that says what matters is not what something is, but how it connects to everything else. This is not mysticism. It is a revolution in physics. It means that mass might emerge from how particles resist change in entangled systems, that energy could arise from symmetries in the code, that gravity itself, the gentle bending of space-time, might be an emergent force, the statistical result of how quantum information behaves across a horizon. Physicist Eric Verlinde has proposed such a theory, entropic gravity, in which gravity is not a fundamental force, but the thermodynamic tendency of systems to maximize entropy. In this view, when a mass appears to curve spacetime, what's really happening is that information is rearranging itself to reach equilibrium. The apple does not fall because the earth pulls it. The apple falls because the universe is correcting an imbalance in its code. These are bold ideas, unproven but tantalizing, and they are part of a broader movement in theoretical physics, the shift from particles to patterns, from fields to information. Physicist John Archibald Wheeler said it best: from bit. Every particle, every field, every force arises from binary choices, from yes-no questions, from the quantum flow of information. If this is true, then black holes are not anomalies. They are windows. They reveal the inner workings of the universe's operating system. They test our understanding of entropy, time, locality, causality, and they show us where our theories crack, where geometry fades and computation remains. But the threads do more than weave reality. They may also unify it. Because the quantum connections that form space-time also connect us, not metaphorically, but literally. The particles in your body were once entangled with particles in stars. The heat of your breath is encoded in the sky. The universe is not a collection of things, it is a network of relations. And this network has no center, no privileged point, no master node. Every bit depends on every other. This is why information is never truly lost. It's just redistributed, hidden in correlations so deep, so high-dimensional, we mistake them for silence. This is why the paradoxes of black holes, loss, duplication, firewalls may all dissolve when we understand that the code is never local. The black hole does not need to store all information in one place. It distributes it, holographically, across the boundary. The information is smeared, scrambled, but recoverable in principle. And perhaps this is true of us too. Our lives, our memories, our footprints in time may be written in the code of the cosmos, not erased by death, not vanished by entropy, but folded into the fabric like whispers into a song too vast to hear. Black holes show us the extremes, but in doing so, they reveal the ordinary in new light. That space is fragile. That time is emergent. That reality is less about things than about the way things relate. And that behind it all, a code runs, silent, perfect, alive. Next, we listen for its footsteps, in the ripples of space-time itself, in the waves that echo from collisions in the dark, in the tremors that speak across billions of years. The universe has no silence. Even when it seems quiet, when space appears still, when the stars drift like lanterns in a void too wide for sound, something is always moving, something is always breaking, and somewhere in that darkness, two monsters are circling. Not stars, not planets, but black holes, invisible, insatiable, ancient. Their orbits are slow at first, like dancers cautious of the dark, but gravity is patient. It pulls, it insists. The circles tighten, the motion accelerates, and then without light, without fire, they collide. And the universe shudders. Not with noise, not with light, but with the trembling of space-time itself. These are gravitational waves, ripples in the fabric of reality, stretching and compressing the cosmos as they go. And though they move through us constantly, we never feel them. They are unimaginably subtle, like the echo of a whisper across a billion light years. Yet they carry the signature of the most violent, most mysterious events in the universe. In 2015, for the first time in human history, we heard them. A century earlier, Einstein had predicted their existence, buried in the math of his general theory of relativity, but he didn't think we'd ever detect them. The distortions were too small, the sources too far. The math said yes, but the world said maybe not. Until LIGO. The Laser Interferometer Gravitational Wave Observatory was built to do the impossible, to measure changes in distance smaller than a proton. Twin observatories in the United States, equipped with laser arms 4 kilometers long, capable of detecting movements 1/10,000th the width of a nucleus. For years they waited. And then, on September 14, 2015, the silence broke. The wave that reached Earth had traveled 1.3 billion light-years. It began with 2 black holes, each over 30 times the mass of our Sun. They had danced for eons, spiraling closer. In the final moments, they circled each other dozens of times per second at half the speed of light. And then impact, merger. One became one, and 3 solar masses of energy were released instantly as gravitational waves. Think about that. 3 suns, gone in a fraction of a second, not as light, not as heat, but as pure distortion of space. LIGO caught that ripple, and for the first time we confirmed what black holes do in the dark. Since then, we have heard dozens of such collisions, each one a cosmic fingerprint, a deep bass note from the dark symphony of gravity. The data gives us more than confirmation, it gives us insight. Because gravitational waves carry no interference, they pass through matter without resistance. They are unfiltered, unscattered, pristine messages from places no telescope can reach. When light fails, these waves succeed. And they tell us that black holes are more common, more varied, and more complex than we thought. We've found mergers between heavy black holes, light ones, and even asymmetric pairs, where one is twice the mass of the other. We've found black holes spinning wildly, tilted oddly, behaving like celestial tops, wobbling as they die. We've even begun to detect neutron-star mergers and the strange hybrids they create, like black hole neutron-star collisions, whose violence may forge the heaviest elements in the universe: gold, platinum, uranium. These events mark the death throes of matter, the final dance of gravity unopposed. But for black holes, it is not an end, it is a beginning. When 2 black holes merge, the result is a larger black hole, a newborn with a ringing shape. The final object vibrates with a kind of gravitational resonance known as the ring-down phase. It's like a struck bell, quieting over time, smoothing into symmetry. These ring-downs match the predictions of Einstein's theory almost perfectly. They allow us to test general relativity in its most extreme environments, curved space-time so fierce it folds inward on itself. So far, the theory holds. But we are only beginning. What we haven't yet detected but long to is the whisper of something new, gravitational echoes, tiny reverberations that might suggest a structure at the edge of the black hole, a quantum fuzz, a firewall, or some holographic skin where information is stored. If such echoes exist, they would upend our understanding of the event horizon. They would be signs that quantum gravity is at work, that black holes are not perfect voids, but messy, information-rich creatures. To hear these echoes, we need more data, better detectors, quieter instruments. LISA, the Laser Interferometer Space Antenna, is a planned space-based gravitational wave observatory set to launch in the 2030s. It will be sensitive to lower frequency waves, the kind produced by supermassive black holes merging at the hearts of galaxies. And that's where things get truly epic. Because the collisions LISA will detect aren't stellar mass black holes. They're millions, even billions of times the mass of the Sun. Their mergers don't just ripple space, they reshape galaxies. These titanic events may tell us how structure formed in the universe, how galaxies grew, how the largest black holes came to be, not as quiet seeds, but as products of cosmic violence. We suspect that when galaxies merge, their central black holes spiral together too. Over millions of years, they fall toward each other, scattering stars, creating waves, and finally merging into one. These collisions may release energy that outshines all the stars in the galaxy, if only we had the eyes to see it. Soon we will. And with every wave detected, we not only confirm black holes, we characterize them, we weigh them, we map their spins, their speeds, their orbits. We learn how common they are, how early they formed, how the universe builds complexity from the simplicity of gravity. And yet, what's most profound is not just what we learn from black holes, but what we learn about the fabric of the universe. Gravitational waves are a different kind of messenger. They don't bounce, they don't scatter, they don't dim or fade with dust. They pass through stars, gas, and galaxies like ghosts. That makes them perfect time capsules, direct records of ancient events, traveling for billions of years before arriving at Earth. When we detect them, we don't just observe the past, we receive it, intact, unblurred. It's as though the universe preserved a memory just for us. And more than light, more than sound, gravitational waves may be the purest signal we ever detect. Even now, beneath your feet, they pass, every day, every hour. The Earth stretches and compresses ever so slightly as these ripples flow through space. You don't feel it, but the planet moves, the fabric shifts. The cosmos is not still. It hums. It breathes. It remembers. And black holes are not just destroyers. They are orchestras, every merger a note, every echo a chord, every ripple a secret. A secret we are just learning how to hear. Next, we travel not through motion, but through stillness. To the hearts of galaxies, where black holes don't collide, they anchor. And in their shadows, the universe builds itself. In the deep quiet of the cosmos, beyond the glitter of stars and the chaos of collisions, there is a kind of stillness, a waiting, a center. At the heart of almost every galaxy, from small spirals to vast elliptical giants, lies a black hole. Not just any black hole, but 1 millions to billions of times the mass of our Sun. These are the supermassive black holes, and far from being passive anchors, they are the architects of galaxies. It's a strange idea. Black holes, by their nature, are the ultimate erasers, swallowing matter, energy, even light. They seem like cosmic dead ends, but the truth is far more nuanced. These titanic objects, silent and invisible, appear to be crucial to the very formation and evolution of galaxies themselves. And the question is no longer whether they're connected, it's how deeply. Let's begin in the center of our own galaxy, the Milky Way. Here, buried in the dense fog of stars and dust, lives a black hole called Sagittarius A. It has a mass of about 4 million suns, compressed into a space smaller than our solar system. We cannot see it directly, it emits no light, but we see what it does. Using infrared telescopes and decades of precise observation, astronomers have tracked stars whipping around an unseen point, orbiting at speeds that defy gravity as we know it. One star, known as S2, completes a full elliptical orbit every 16 years, reaching speeds over 7,000 kilometers per second. Only one explanation fits: a compact mass so dense, so dark, that nothing else could survive as the cause. Sagittarius A is a supermassive black hole, sleeping for now. But across the universe, some of its cousins are not so quiet. In certain galaxies, we see the signs of active galactic nuclei, cores that blaze with more energy than 1,000 Milky Ways combined. These are powered by supermassive black holes feeding. As matter spirals inward, it forms an accretion disk, a swirling superheated maelstrom of gas and dust that shines across the electromagnetic spectrum. Friction and magnetic forces heat this disk to millions of degrees. The light it emits can outshine the entire galaxy, and from the poles of some of these black holes erupt relativistic jets, narrow beams of particles traveling near the speed of light, stretching across thousands of light years. We call the most extreme of these engines quasars, short for quasi-stellar radio sources. They are among the brightest objects in the universe, visible from billions of light years away, and they tell us something extraordinary. Supermassive black holes formed early. The most distant quasars we've detected existed when the universe was less than 1 billion years old. That means black holes, at least some of them, grew fast. Too fast, perhaps, for the standard theories of star death and accretion alone to explain. Did they form from the collapse of the very first stars, the so-called population 3 stars, giants hundreds of times the sun's mass? Or did they emerge directly from giant clouds of primordial gas, bypassing stars altogether? We don't yet know, but what's clear is this: black holes and galaxies grow together, and the evidence lies in a quiet correlation. Across thousands of galaxies, we find a consistent relationship between the mass of the central black hole and the velocity of stars in the surrounding bulge. This is known as the M-sigma relation. In simpler terms, the bigger the galaxy, the bigger the black hole. Not in mass alone, but in influence. This is puzzling, because the black hole, even at millions of solar masses, is tiny compared to the galaxy. Its gravitational pull dominates only a small central region. So how does it know about the rest of the galaxy? How does the galaxy know about it? Something deeper is at work. Many physicists and astronomers believe that supermassive black holes regulate the growth of their host galaxies through a process called feedback. When a black hole feeds too quickly, the radiation and jets it emits can heat the surrounding gas or even blow it out of the galaxy entirely. This limits how much new star formation can occur. In this way, the black hole becomes a kind of cosmic thermostat, ensuring that the galaxy doesn't grow too fast or too chaotically. It's a delicate dance. Accretion fuels power. Power regulates stars. Stars govern accretion. A loop of cause and effect, fine-tuned over cosmic time. And sometimes that loop breaks. There are galaxies, rare and ancient, with multiple black holes at their cores. These are often the product of galactic mergers. When two galaxies collide, their black holes begin to spiral toward one another, trailing chaos. Stars are flung outward, gas is compressed, igniting waves of star formation. Eventually, if the conditions are right, the black holes merge, releasing gravitational waves that echo across the cosmos. But sometimes, in the chaos of interaction, one black hole is flung away, ejected by gravitational recoil. A rogue black hole, drifting through intergalactic space, homeless, silent, carrying a galaxy's secret in its wake. It's even possible that the center of the Milky Way once experienced such a drama that Sagittarius AC is not the first, but the survivor. These are not fringe ideas. They're supported by simulations, observations, and the growing catalog of black hole mergers detected through gravitational waves. The more we look, the more it becomes clear. Supermassive black holes are not side effects of galaxy formation. They are co-creators. This shifts everything. We tend to imagine black holes as aftermaths, the corpses of stars, the dead centers of chaos. But supermassive black holes might be seeds, not the end of a process, but its beginning. Some cosmologists propose that the very first structures in the universe formed not from stars, but from primordial black holes born moments after the Big Bang, when density fluctuations created pockets of collapse. These black holes could have attracted gas, forming the first galaxies. They might even serve as a partial explanation for dark matter. If enough small, ancient black holes exist, their gravity could account for some of the unseen mass in the universe. Still, This remains speculative. Observational evidence is scarce, but the idea lingers that before there were galaxies, before there were stars, there were already wells in space-time. And around these wells, matter gathered. Light followed, structure emerged, and the universe found its form. We often seek meaning in brightness, in stars, in suns, in light, but perhaps the true architects of the cosmos are the dark things, the silent things, the voids so heavy that they bend everything around them into shape. Supermassive black holes don't build with hands, they build with gravity. They do not shine, but they guide the light. They do not speak, but they sculpt the music of galaxies. And in this silence, in this gravitational governance, there is something beautiful. It reminds us that even the darkest things can give rise to structure, to harmony, to meaning. From the first star to the last galaxy, black holes have shaped the universe, not with destruction, but with design. And as we near the end of our journey, we look to the question that began it all. If black holes can birth galaxies, process information, and reshape space-time, could they also be the bridge between beginnings and ends? What lies before the black hole and after? To answer, we must walk the edge of physics itself, to the border where theory dissolves and speculation begins, to the farthest limits of time. Stand at the edge of a black hole and look inward, and you will see nothing. Not because it is empty, but because the laws you've always trusted begin to fail. Time slows, space curves, direction loses meaning, cause and effect begin to blur. It's not just that light can't escape, it's that certainty can't. This is where physics surrenders its confidence. This is where the universe ceases to be explainable in simple terms of before and after. But even here, perhaps especially here, questions bloom like galaxies. What came before the black hole? What, if anything, lies beyond it? And could black holes connect us to something older, deeper, stranger than time itself? To ask what came before is to step into treacherous territory. It assumes that time is linear, that it flows like a river, and that events unfold like dominoes. But inside a black hole, that metaphor collapses. There, time doesn't flow around things, it points inward toward the singularity. In a sense, crossing the event horizon means crossing a temporal threshold where time no longer ticks forward but funnels down. The singularity is not a place you approach in time, it is a moment you fall into, one you cannot escape or delay. It's no longer you're falling towards something. It's time itself is falling with you. So when we ask what lies before, we are not merely asking about an earlier moment, we're asking about what gives rise to time at all. Some theories suggest that black holes may be recyclers of the cosmos, that beyond the singularity, instead of a final punctuation mark, lies a bounce, a place where matter is compressed not into nothingness, but into a seed for something new. This leads to the idea of a white hole, where a black hole is a region from which nothing can escape. A white hole is a region into which nothing can enter. Instead of pulling everything in, it pushes everything out. It is the mirror image, the temporal inverse, a place of explosion, not implosion. White holes remain entirely hypothetical. No one has observed one. But in some models, particularly in loop quantum gravity, black holes do not end in a singularity. Instead, quantum effects prevent total collapse, and a bounce occurs, potentially giving rise to a white hole. In this speculative framework, the interior of a black hole is not a one-way trip to oblivion, but a tunnel, a bridge, a wormhole, perhaps leading to another region of space, or even another universe. That leads us into even deeper speculation, the possibility that black holes are not just ends, but beginnings, that each black hole might be a kind of cosmic womb from which new universes are born. This is the black hole cosmology hypothesis, and it is as bold as it is beautiful. It suggests that our own universe could be the interior of a black hole, formed in another higher dimensional universe, that what we call the Big Bang was not the absolute beginning, but the emergence of space and time from the other side of a collapse. Think of it, every black hole you see could be the start of a new universe with its own physics, its own dimensions, its own passage of time. A multiverse, not of parallel worlds, but of nested realities linked through the throats of black holes. It's elegant, it's speculative, and it's entirely unproven. But it confronts a deeper question. Is the singularity truly singular? In general relativity, the singularity is a place where curvature becomes infinite, where density skyrockets, where our equations no longer make sense. But most physicists agree that this infinity is a sign that our theories are incomplete. What we call a singularity may not be a point of infinite density, but a place where the classical description of space and time breaks down, where quantum gravity must take over. Unfortunately, we don't yet have a complete theory of quantum gravity. String theory, loop quantum gravity, and other approaches offer glimpses, but the full picture remains hidden. What we do know is this: the closer we approach a singularity, the more we must abandon our familiar assumptions. Space becomes granular, time becomes ambiguous, particles cease to be points, waves become probabilities. Reality shimmers with uncertainty. And now, consider the end. Black holes are not eternal. Stephen Hawking showed that black holes emit radiation, tiny amounts, but enough. Over time, they lose mass, they shrink, they fade. A solar mass black hole might take 1060 SAB years to evaporate. A supermassive one could last far longer. But given enough time, even the mightiest black hole will radiate its last bit of energy and disappear. Or will it? If black holes evaporate entirely, we face the information paradox again. Is everything they consumed truly lost? Modern physics leans toward no. Somehow the information must be preserved, perhaps scrambled in the Hawking radiation, or released in a final burst, or encoded on the horizon. But no one knows for sure. In the far, far future, a trillion years from now, the last black hole may vanish. The universe may go dark, stars long extinguished, galaxies faded into red ghosts. And yet, the ripples of black holes may still echo, their imprint etched into the shape of space itself. They are not merely events, they are authors. Their collisions shaped galaxies. Their presence regulated stars. Their gravity sculpted the cosmic web. Even their end may write the final chapter of the universe. And what of us? We are not separate from black holes. The same laws that govern their behavior govern ours. We are made of atoms born in stars that circled black holes. We walk on worlds that orbit in systems carved by their presence. Perhaps in some strange poetic way, we are black holes, not in mass but in mystery. Our thoughts are events with no light. Our memories curve time. Our inner worlds, too, contain singularities, moments that changed us, from which there was no return. We carry paradoxes. We wrestle with information. We seek beginnings. We fear ends. But just as the black hole contains more than darkness, so do we. So here, at the end of our journey, we look back. We've fallen past the event horizon. We've watched time slow and light bend. We've listened to collisions in the void. We've glimpsed the quantum code. We've wondered whether black holes are tombs or tunnels. And through it all, one truth emerges. Black holes are not the end of understanding. They are the beginning. They challenge every law we believe in, every intuition we trust. They reveal where our models work and where they fail. They unite opposites, creation and destruction, time and timelessness, order and entropy. They are the universe looking at itself folded inward. And perhaps that is what we are too. The cosmos, contemplating its own code. Gravity, dreaming in the shape of consciousness. Information, becoming aware. So now, breathe. Let go of falling. Let go of fear. You are not separate from the stars, or the void, or the mystery. You are part of the same unfolding. And if black holes hold the secret to time and space, then so do you. Close your eyes. The gravity within you is enough. Let the universe spin, gently and silently, as you drift beyond the event horizon of thought, into rest.